After this, at 4 o'clock in the bistro, I'm going to be leading a discussion section, questions and answers, and
If I'm still standing.
if he's still standing, and if he's done with this talk.
I'm not. You're confusing me with David Gross. Can I take this memory stick out of here? Is there some reason why it's still in here? Okay. All right. This is Colloquium is a little unusual, I think. It's a little less concrete than I would like it to be. The genesis of it was I had been thinking about writing a review article about a subject which I'm very interested in, Coleman DeLuccia Tunneling and the phenomenology of it, and how to organize that phenomenology using something that my colleagues and I call FRW-CFT duality. The subject was getting a little bit away from me. I was having trouble organizing it. Whenever that happens, what I usually resort to is finding myself a captive audience and presenting lectures on it to some poor, unsuspecting people who think I'm really there to either entertain them or to educate them. No, I'm here for my own, completely my own purposes. So that will account for some of the peculiarities of this lecture. Fortunately, I'm old enough that my skin is made out of elephant hide, and there's little you can do to me to punish me for this lecture. Anyway, what I thought about when I started to prepare the lecture, or this series of lectures, I don't know how many there will be. I will lecture until I'm finished, whether or not there's anybody, whether there's an audience left. I don't mean today, I mean when I continue. But when I thought about organizing it, I realized that I'm kind of used to talking to a bunch of people who think about exactly the same things I think about all the time, and that most likely there are people here who don't think about those things all the time. And it was probably necessary to, if I was going to give a colloquium, as Neil asked me to do, to keep it much more general, at least the first time, and discuss what the problem is, what the set of issues are, and before getting into any kind of technical questions. So I'm going to do that now, and later on we can get into more technical questions about the meaning of this concept, which I'm very excited about, called FRW-CFT duality. But what it all has to do with is, as I said, the phenomenology of a universe that was born out of the nucleation of a bubble. If you know who Coleman and DeLuccia were, well, some of them are, some of them were, then you know about tunneling and false vacuums and all that sort of stuff. If you don't know, I'll try to tell you. The use of the term standard model is what the rhetorical device to make these systems practically correct. There are plenty of people around who don't believe the standard model is all our standard. I'm not just only in this room. Okay. Yeah, okay, good. So there are plenty of serious people with good credentials. Nevertheless, I'm going to assume. I'm going to make the assumption that what is usually called the standard model is in fact correct. That, of course, can be debated, and start discussing if it turns out to be correct, if we know it's correct, what comes after. So the first question is, why does anyone think that there is something beyond the standard model of cosmology? Or what is the standard model, first of all? Standard model is simply that we live in a world with a small cosmological constant lambda. Cold dark matter is the dark matter of the universe. We don't know exactly what it is, but it's particles. That's the assumption, that it's particles. particles very weakly interacting kind, and finally inflation. It's of course inflation which is the most contentious of these, and I'm going to assume that this is correct. Okay? Why should we assume that there's anything beyond this? Perhaps the world just began with inflation. And the answer, I think, is pretty much the same as the answer for ordinary particle physics. Why do we think that there's something beyond the standard model? I would say in particle physics we know there's something beyond the standard model. But the simplest answer is because the energies of the standard model are just so very low that they couldn't possibly be the end of things. In fundamental units, the energies of particle physics are 10 to the minus 19th, 18th, 17th. And it's just unreasonable that the flow of reductionism will end at such a very low energy. The answer is pretty much the same about inflation. We usually think of the inflationary energy density as enormously large, and of course, by comparison with anything in this room, it is enormously large. But when measured on the Planck scale, the energy density during inflation could not have been bigger than about 10 to the minus 14th. If it was bigger than 10 to the minus 14th, the universe would be filled with gravity waves and probably worse things than that. And we know that that's not there. So the energy density measured in fundamental units during inflation was very small. As I said, 10 to the minus 14th. And it just seems unreasonable to assume that that is where the world began. It must have began in some way that involved higher energy densities, perhaps a singularity, perhaps an ekpyrotic collision of some sort, but something that involves more energy than this 10 to the minus 14th. All right, the particular view of things that I'm going to talk about, which in the circles that I move in, it's almost considered standard. And once I move out of those circles, it tends to be viewed with a great deal of skepticism. It's called eternal inflation and a landscape. So let me tell you what my assumptions are. There are basically two assumptions that go into this, really only two assumptions, and the rest pretty much flows out of it more or less smoothly. The first assumption is that there does exist a very elaborate and complicated landscape of vacua. This is motivated by string theory, but it may well go way beyond string theory. It may be many vacua that can't reasonably be described by string theory. But at least string theory is a model or a construction which shows us how it can be that the space of possible vacuums, the space of blueprints, if you like, for universes is enormously large. And of course, the way it happens is that the compact directions of string theory can be twisted, deformed, wrapped, fluxes put on them in an enormous variety of ways. I'm not going to get into that in any depth, except to put this picture in front of you, which is not a legitimate picture of a Calabi-Yau manifold. I think it's some artist's rendition of it. It shows, and of course it's in the wrong number of dimensions. Calabi-Yau manifold should be in 6 dimensions. This is drawn in 2 dimensions. But it gives you some idea of the general complexity of the constructions that string theorists use to describe small distance structure of space-time. The colored lines on it can either represent fluxes or branes wrapped on cycles and so forth. And the point is that there's an enormous variety of ways of rearranging this thing. I won't even try to quote a number, but the number is far bigger than astronomical. Number of possible arrangements. And this is what is called the landscape of string theory. Now, the landscape of string theory can also be thought of as an energy landscape. You can move these things around, twist them, deform them, and there are certain stable configurations. In between those stable configurations are hills and valleys. It is believed that this space is all connected in the sense that transitions can happen between different vacuums. That's an assumption I'm going to make. And so, roughly speaking, well, it doesn't look anything like that, of course, but that's a cartoon of a complicated energy landscape. Is it a pointer? Oh, this is the pointer, right? Yeah, okay. Right, so lots and lots and lots of hills and valleys. The valleys are stable minima, and they're the kind of stable vacuums that, that can be stable. Okay. Now, we apparently live, in this view of things, at the end of a kind of shallow plateau. This shallow plateau in the landscape is the place where ordinary inflation took place. Ordinary inflation is the kind that would explain the spectrum of density fluctuations and so forth, the kind that's by now in textbooks. And it has a certain width. It's kind of a ramp, sort of a roller skating ramp that you roll down, but you roll down slowly, called slow roll inflation, until you get to the end of that ramp. And the end of that ramp, or that plateau, is where we are now. Okay, this is one basic set of assumptions. The existence of a landscape connected to where phenomenology begins. Phenomenology begins over here. This is where slow roll inflation starts. And you can see why one might be skeptical about the slow roll inflation being the starting point of everything. It's just too low in energy. The second assumption that I will make, besides the existence of such a landscape, is that, in fact, we started up much, much higher on this landscape. In other words, we started somewheres in it, unknown place. This landscape is largely unknown and maybe even unknowable because it's so complicated. But that we started in some configuration. And when I say start, I don't mean ultimately start. I know nothing about the origins. I just mean that we can trace ourselves back a little bit further to some point on the landscape which is a good deal higher. Well, how did we get from here to here? Well, you start on the top of a hill, you'll naturally roll down. What's the chances that you roll all the ways down to where we want to get started without encountering a local minimum? Oh, one thing which is important in this context is that in cosmology there's lots of friction. It's a rolling problem, but it's a problem in the presence of loads and loads of friction. That friction tends to make you ride down, and one might expect, I would expect, that with such a complicated landscape, you'll arrive in some local minimum at a relatively high altitude long before you'll get down to here. That to me seems entirely reasonable. And if you do get down to some local minimum, you're going to get stuck there. You're going to get stuck there classically. You're going to get stuck there forever. Quantum mechanically, you may tunnel. Not you may tunnel. Sooner or later, you will tunnel out of local minima. And you'll tunnel from one minimum to another minimum to another minimum. And if you're lucky, you'll get down to the point in the landscape where we began our phenomenological existence. Now, you might ask, by what piece of luck did we get to here and not over to here someplace or over to here someplace? Why do I think why should we have gotten to this particular place, which we will see is a sort of fairly fine-tuned and special kind of thing? And the answer has to do with what is called eternal inflation. One could say it a different way. The question of whether this process, which takes you down the hill, is a process which should be thought of as a linear process in series or a process in parallel. I'll explain what I mean by that. But first, here's a picture of space-time, stable de Sitter space-time corresponding to starting in some minimum. You start in some minimum. Vertically is time, horizontally is space. This is a conformal diagram for de Sitter space, for those who recognize it. For those who don't recognize it, just think of time as flowing upward. And I'm using coordinates. In fact, the amount of time from the bottom to the top is infinite, but I'm using coordinates in which equal measures of proper time are represented by the sequence of light lines there. So the total amount of time from bottom to top is infinite, but the whole thing got drawn on a finite piece of a blackboard. In such pictures, light rays move on 45-degree angles, even though the space doesn't look like ordinary flat space-time. It's de Sitter space. All right, that's where you begin. At some local minimum, with a rapidly inflating, this is a rapidly inflating space, extremely rapidly inflating. And in such rapidly inflating spaces, tunneling can happen. Tunneling does not mean that the tunneling goes back to the picture which I drew before. Tunneling from one minimum to another. The way that tunneling does not happen is that the entire universe suddenly goes from one state to another. That would be extremely improbable for a fluctuation to happen in which the entire inflated universe suddenly makes a jump from one place to another. Tunneling of this type is a thing which happens locally. And when it happens locally, a little bubble nucleates, slice it horizontally, a little bubble nucleates. Inside that bubble is a different vacuum, and that vacuum begins to grow. The bubble begins to expand until eventually it becomes very, very large, in fact, infinitely large, and terminates itself in the same way that this vacuum terminated over here. It doesn't really terminate. It's just a drawing to get it all onto a finite portion of the blackboard. Incidentally, there is an invariant and real meaning to the fact that in de Sitter space, the end of time is space-like. That is an invariant fact that, that has a particular meaning. If it means something to you, good. If it doesn't mean something to you, not important. Okay, now, once a tunneling happens from one point on the landscape to another, inside that bubble, we're now on another point on the landscape, tunneling can happen again. It can repeat. So in that sense, an observer moving along sees a series of different vacua, a series process, one to the next, to the next, to the next. But at the same time, if we only knew exactly what time meant, at the same time, other bubbles can nucleate, and the whole process becomes a parallel process as well as a series process. It becomes a parallel process in that many things can be happening at the same time, and in each one of these bubbles, parallel processes can be happening. By parallel processes, I mean branching, a kind of branching process. And personally, I see no way to avoid this. If the assumption of a landscape and the assumption of metastable vacua is correct, and we did start up high on this landscape, frankly, I don't see any way to avoid this. This looks to me very inevitable. Maybe I'm wrong. All right, it's parallel in the sense that many things are going on at the same time, but a particular observer moving from bottom to top simply experiences a series of vacuums. All right, so every observer, real observer, experiences a series. The whole global structure is a parallel structure. And so both are happening, series and parallel. It's because of this parallel character, that we can say someplace in this vast multiverse of possibilities here, someplace we will arrive at the desired kind of vacuum that we live in. Not every observer will wind up on this broad plateau with inflation, with the slow roll inflation and so forth. Perhaps a very, very small fraction of them will, if we knew how to define fractions in this context. But somewhere, with enough of this stuff happening all over the place, some places will wind up being the kind of vacuum, assuming that it exists on the landscape, the kind of vacuum that I described. So that, if you like, is the basic set of hypotheses, or the two basic hypotheses, a big landscape and that we started up high on it. Okay, now we come to the terrible scarlet letter, the A word, the anthropic idea. With this, assuming all of these things, and which was not very much, just two basic assumptions, there is no way to avoid some anthropic considerations. If there are many, many patches of space, and the landscape is hugely large with all kinds of things in it, surely there are places which are totally inhospitable to life. Those places are not the kind of place we live in. That's the kind of place we live in is the kind of place which is hospitable to life. That's the whole content of the anthropic principle. It is as sensible in this context, assuming this is true, it is as sensible as saying we live on a planet which is the right distance from the sun because we couldn't live on a planet which isn't the right distance from the sun. So anthropic reasoning will inevitably be part of such a story. All right, let's go to the cosmological constant. The cosmological constant is, of course, a great puzzle, a puzzle being why is it so small? In natural units, it's 10 to the minus 123. What's the reason for that? And the answer is nobody has a mathematical reason for it. There is no known explanation of the smallness of that number. That has led people, myself included, but especially Steve Weinberg, 20 years ago, more than 20 years ago, to speculate that maybe the reason that the cosmological constant is so small is because simply those vacua in which we could exist would necessarily have to have a small cosmological constant. With a landscape as big as the one from string theory, one might argue there will surely be some small fraction of them with small enough cosmological constant. Where can we live? If we can make an argument that we can't live in a world with a larger cosmological constant than we have, well, then we might argue that the whole thing is anthropic. That led Weinberg to investigate the question whether a larger value of the cosmological constant would be sufficiently unhealthy that we couldn't be here. And of course, the answer, I'm sure many of you know, is that he discovered that if the cosmological constant was maybe 100 times bigger than the observed value, that structure couldn't form. Structure couldn't form means stars, planets, galaxies couldn't form for the simple reason that a cosmological constant is a form of repulsion, and it would have overwhelmed the tendency for things to collapse in the early universe. I'm going to take this to be a correct argument. And again, of course, this can certainly be reasonably questioned. Yeah.
It would be that CC is actually very big, but we have the wrong theory of gravity. So for some reason, we don't see the gravitational effect of a huge CC. So what do you think?
Possible. Okay, that's possible.
But then how do you define different theory of gravity? It's not even all different topics.
We each come equipped with our own prejudices, and I will freely admit that I have prejudices. Whose prejudices are right? That's what this is all about, to try to test these ideas. In fact, I'm not going to come to you with ideology and tell you the reasons why I believe this to be right. What I really want to emphasize is the importance of testing these ideas. Can they be tested? And if so, what do we have to do to test them? How do we organize data to make sense out of it in this kind of context? So I really am interested in the phenomenology of these ideas. Now, I will tell you from the beginning, yeah.
Why is cosmological constant so large? 10 minus 240.
Yeah.
Whereas the energy density is possibly precise to the universe.
We don't, look, you're asking the right question. The right question really is, what is the measure of this space?
Right.
Right, and nobody has sensible answers to this, as you well know, I'm sure. That question didn't come out of the blue, or the question is one that we're all very puzzled about. What is the probability measure on this space? And let me say right now, since I probably will forget about the question, I'll purposefully forget about the question, that this question of what the measure is probably the biggest potential Achilles heel of this whole story. The inability to be able to come to a conclusive statement based on fundamental principle that here's the probability distribution. That, I think, it really is the potential Achilles heel. But it's a theoretical question to try to find some kind of argument for a measure. And I'm not sure that people have thought about it long enough and hard enough. But we'll find out. I don't know.
So just to press you a little bit on this point, I think what many of us here are unhappy with is the phrase, the anthropic solution to the cosmological constant problem.
Which is not one that I used.
No, so I'm asking you, do you endorse that phrase, or do you think that's a...
You can ask me whether deep in my heart I endorse it, or whether I'm standing here endorsing it for you.
No, deep in your heart.
Deep in my heart, I do. Yes, deep in my heart, I do. But I fully recognize that this is something, but the most important question is to try to test these ideas. Is to try to test these ideas, to subject them to tests, and that means organizing some framework in which to address them.
But the problem is, if people claim a solution to a problem,
Yes.
that means that anyone else is actually trying to solve it. So it feels it's pointless because everybody thinks
You're
it's
trying to
solved.
drive me into an ideological discussion. I'm going to do it.
No, I just want your opinion. It's a solved problem or not? And I guess you're saying it's not. So that's
No, I'm not saying anything of the sort. I'm not saying it's a solved problem. I'm not saying it's not a solved problem. There's a potential hypothesis there which is incomplete, which doesn't entirely hold water. It's a leaky hypothesis. It needs to be, the leaks have to be filled in theoretically, and then it has to be tested observationally. All right? To my way of thinking, to me, this is the most likely framework for beyond the standard model, likely existing. But you can, I don't care whether you believe it or you don't believe it, as long as you spend a little bit of time trying to figure out how to test it. If you're against it and you hate it, try to figure out how to kill it. Okay? That would be very, very useful to try to do, because in the process of trying to figure out how to kill it, you might just do the opposite, but I don't know. Or the opposite, In the process of trying to test it because you believe it, you might kill it. I'm not even claiming that.
You're not.
Of course not. Yeah, no, in principle, I think, yes, there's a possibility that it can be killed, but we have to be lucky.
Okay.
We have to be lucky with the numbers. It's very much like the standard model of particle physics. Can we test supersymmetry? Can we test where a lot of people think is the next layer? Yes, if we're lucky. No, if we're not lucky. What does lucky mean? The numbers happen to be in the right ballpark where we can measure them. How likely is supersymmetry? Well, if you went around the room, you'd probably get numbers from. I bet there's nobody here who would say 100%. There are probably nobody who would say 0%. And you get a whole range of numbers in between. And therefore, the numbers don't really mean anything. What do? You go and test it. All right. Now, I think not enough thought. I don't mean to say that people have not been thinking about it. I think there's not been enough thought about how to test it, and too much thought about how to ideologically argue about it. Okay, so I could quit right here and be happy with what I've said. Okay, let's talk about what is seen inside one of these bubbles. Inside one of these bubbles is surprisingly, depending on whether you've been through Coleman and DeLuccia's ancient paper or some other papers that came afterwards, in particular papers that our esteemed director here has written. Indeed, he has. And actually, the first place I ever read that the interior of a bubble is an open FRW universe, I think, was in a paper that you wrote. I'm not sure. I don't even know if Sydney and his collaborator knew it. Well, that for sure. Yeah, that for sure. Okay. All right. It's a curious fact. You know, the standard and traditional idea of cosmology is that the old idea that goes back to Einstein and even before Einstein is that the universe is closed and bounded and expanding, and it looks like a balloon. It was quickly recognized that there were three possibilities: open, flat, and closed, closed, open, and flat, positively curved, flat, and negatively curved. And the curious thing is that bubbles formed through the Coleman DeLuccia tunneling mechanism from the inside. From the outside, they just look like expanding bubbles. They come and hit you in the face. From the inside, they don't hit you in the face because they're moving away with the speed of light. And what somebody on the inside sees is an open, negatively curved FRW infinite universe. And the easiest way to see that is just to take this patch and to foliate it with a series of space-like surfaces which follow lines of constant energy density. If you follow lines of or surfaces of constant energy density, they look about like this. If you remember from my first drawing, the metric of space-time diverges up near the edge up here. And that means that very, very tiny distances up near this point, very tiny visual distances, correspond to enormously large spatial distances or space-time distances. And that's the reason that these slices through here are infinite. They're infinite. They diverge at these points over here. These are not points. This is a two-sphere, the two-sphere of the sky. I have drawn the diagram as it would look if the eternal future and the far future was flat space, was zero cosmological constant. If it's not zero cosmological constant, in particular, if it's positive cosmological constant, this gets rounded out a little bit, but that's not so important for my discussion today. So these are infinite spatial slices here, and an observer in here would believe that they are in an open FRW universe. Looking back to what you might think is this expanding domain wall, they would really see the Big Bang. This is the Big Bang. This is the hot place where we all came from. And time just progresses along these surfaces here. Okay? Now, the interesting fact about these surfaces, which is not too hard to believe just from drawing them, they look like hyperboloids in a Minkowski plane. They're negatively curved. These surfaces are negatively curved FRW. And negative curvature in cosmology has a Newtonian analog. Positive curvature means everything was sent out with below the escape velocity, and it's going to come back and crunch. Flat means everything was sent out with just about the escape velocity. And negative curvature means everything was sent out with greater than the escape velocity. So everything just keeps going and doesn't turn around and recrunch. Now, that's fine. I don't particularly want the crunch, but it's bad if you're a galaxy that's trying to form in the early part of the universe. If you're a galaxy that's trying to form and everything inside you is moving apart with greater than the escape velocity, you're in trouble. You're not going to recollapse and form a galaxy. The galaxies had as their origin very, very minute little density fluctuations. So a lot of outward expansion, a lot of negative curvature would immediately, together with a positive cosmological constant, the argument is the same, outward kinetic energy would be another reason why galaxies would have a hard time forming, where they wouldn't form. So the question then is, how do you get rid of the negative curvature? First of all, why should you get rid of the negative curvature? Not why because we want to have galaxies, but how do you get rid of negative curvature? How do you get rid of too much negative curvature? And the answer is to dilute it. To dilute the negative curvature by a period, this is the only known way, to dilute it by a period of slow roll inflation. This is slow roll inflation that takes place after the bubble is nucleated. And that's the origin, well, that's not the origin, but that's more or less equivalent to saying that after we tunneled out of the earlier vacuum, which I've taken to call the ancestor vacuum, the ancestor vacuum is the vacuum from which tunneling occurred into the phenomenological world, which includes slow roll inflation. We jumped from here to here during this tunneling process. And the question is, how much slow roll inflation took place? Why do we care how much slow roll inflation took place? And why did slow roll inflation take place? Okay. I'm going to tell you that I think the reason is anthropic. The only reason I know of why the potential, the field potential, I think there's a piece missing over here. It's sort of below the radar here. It's the little piece that goes down and ends the inflation over here. Why does this broad plateau exist? And believe me, this broad plateau, you have to stand on your head to make it happen in any kind of sensible field theory. In other words, another way of saying it is it takes a lot of fine tuning to make this broad plateau here. Why did it happen? Why did we pick out from all the places in the landscape one which supported enough slow roll inflation that this negative curvature was diluted away? Okay, well, yeah.
You need specifically slow roll inflation or just a long period of inflation?
A long period is what's usually called slow. Yeah.
No, but you could see at the bottom of the potential.
What's that? Say it again?
You could see at the bottom of the potential and keep inflating. So that's not a slow roll.
Sitting at the bottom of the potential, if the potential has a non-zero cosmological constant, then it's infinitely slow roll.
Well, they don't usually call it a slow roll. So
Sitting at the bottom, no. We know that the ordinary thing that we call inflation is not at the bottom of the potential. We're at the bottom of the potential now. Okay, we're at the bottom of the potential over here. The energy density in the universe is minute. During ordinary inflation, the energy density was many, many orders of magnitude larger. So yeah, there was a period that had to be long enough. That means the potential had to be shallow, and it has to be broad. Okay, how broad and how shallow is a question of fine tuning and that sort of thing.
Right, where you go fast for a while and then you hit a saddle point and you slow down some and then it goes fast for a while again.
You mean after the bubble is nucleated?
Yeah, after.
Yes. Yeah. Oh, yes. Yes. Sure. It's still.
But is that compatible with our other cosmological observations, or?
Yes, I think it is. I think it is. But I think there's probably about a region of about 10 e-foldings here, which is known to be pretty slow roll. Okay, so there is some region in here which is the whole expansion that we need to dilute the curvature could have existed, could have come in fits and starts, as you say. Yeah. But the question is, why did it happen altogether? And the only really known reason, apart from phenomenological reasons, is anthropic, that without it, you wouldn't have diluted the curvature. Not diluting the curvature, everything would be shot out too fast to create structure. So let me just address very quickly the question of how likely is it. Now, I can't answer this because it will involve questions of measure that I don't know how to answer, but we can make up silly models just to get some sense of how unlikely this kind of thing is. I'll just show you a very, very elementary and simple statistical model. Supposing we characterize this potential by 3 parameters: a width, a height, and as I said, the floor of this potential is somehow missing off the screen. So it has a height, a width, and a slope. Just those 3 parameters. Make a box. The height can go from 0 to Planckian, the width can go also from 0 to Planckian, and the slope can go from 0 to 1, or whatever the right parameterization is. And then randomly select points out of this box. Right? This is an arbitrary thing to do. You can then calculate what is the probability, in other words, with a uniform measure on this box, what is the probability that you'll have n e-foldings of slow roll inflation. N e-foldings means that during that slow roll inflation, the universe expanded by a factor of e to the n. And the answer is that it's rather difficult to get a lot of e-foldings. N here stands for the number of e-foldings. And just doing that very, very simple exercise, you find a function which is very peaked at no inflation at all. It's just another way of saying that a common garden variety potential is not going to inflate very much. Right? So it tends to be very, very suppressed. And if you then ask the question, what's the probability that there was enough inflation to satisfy the constraints of observation, which are often said to be more than 60 e-foldings? That's a somewhat arbitrary number, but let's just use it. More than 60 e-foldings, it's just the area under this curve. With this very, very simple model, it turns out to be some number, 10 to the minus 12. Okay, so slow roll inflation is unlikely. But now let's ask another question. What is the anthropic bound? How much slow roll inflation must happen in order not to satisfy experimental observation, but in order that we could be here to make the observations? In other words, in order that galaxies and stars and planets formed. we have to dilute the curvature. We have to have some of the slow roll inflation in order to have things structure form. It turns out that I can't get there. It turns out, surprisingly, that to have structure form, you'll have to have 57 e-foldings, roughly. I think the estimate was 57.5 e-foldings. But the point is that it's fairly close to the observed bound. Now you add, this is anthropic bound, this is observational bound. Now you ask a different question. Given that we're here, given that n is bigger than 57.5, given that we exist on a point in the landscape where structure can form, then what is the probability that n is bigger than 60? And that, in this particular model, is 0.9. Not surprising. I mean, there's nothing surprising about this. My only point is that, as far as anybody knows, this is the only explanation of why there was such a long period of slow roll inflation, why the potential was tuned to 1 part in 10 to the 12th, if you like. Yes.
Okay.
That's a good point. Very good point. Yes.
But of course, if you're changing the potential, that does.
Yeah. You can play with numbers, and you can probably increase the size. Yes, I have. You're exactly right. I have input into this calculation that the primordial density fluctuations was 10 to the minus 5. Thank you.
There was a question over there.
Yeah. You've drawn these potentials with lots of local minima over in the landscape, and then this long ramp going in for slow roll.
Odd.
So why, this is an elementary question, but why is, suppose we tunnel into a basin, but not directly to the local minimum. Why can we not get a slow roll down to the absolute minimum of the basin? Why do we have to have this special structure?
Let's see. Are you asking why this can't just roll down to 0 or something? Or
Why do you have a plateau? You had a plateau.
Yes, it's not about this picture. It's about your drawings of the landscape.
Yes. I think I remember the picture.
Right. So
that is. Oh, sorry. No, this is a probability picture. Thank you. This picture, which has been truncated by.
So suppose we had simply tunneled into the catchment basin of another local minimum.
Here, for example.
Here? Or we've tunneled into what you've got labeled ancestry. We tunneled from somewhere into there.
Yeah, we came there.
There's a flat region around the base of that.
Here?
Right. As we coasted down with all this friction, why wouldn't that give us slow roll inflation?
It's not slow enough.
It's
just not slow enough?
I think it could.
Yeah, it could, but if the energy density was too high here, then we would be in a situation with a large cosmological constant, which would destroy galaxies because of vacuum pressure. So you don't want to be high up here. Well, okay, you don't want to get stuck here. That's not a good place to get stuck and to wind up living. Okay. We want to live down here, but we want to live down here with galaxies and so forth. We don't just want to live down here with a very small cosmological constant. We want to live with a cosmological constant and matter and entropy and galaxies and planets. And for that, as far as I know, the only way to do that is to have this period of slow roll inflation. Okay. And we can discuss that in more detail.
Well, do you want a question?
While we're talking about it, I was wondering why we need the dip at the end at all.
Why do you need a sudden dip? Why can't it just gradually be empty? We need the sudden dip. It's during that sudden dip that vacuum energy is converted into heat and stuff.
Oh, particles.
Particles.
Oh, okay.
Yeah, particles. Right.
I think you don't have to. You just have to have a quadratic potential at the bottom. You don't have to have a dip. You could just have a quadratic.
You say you could have this is the full curve.
Yeah.
You say the whole thing can be quadratic. That's what's called what? Some kind of equation. Stochastic or chaotic or something.
Yeah.
I never remember which is which. Yeah. The problem with that, and in order to make that work, the range of the potential would have to be, the range meaning the width of the field would have to be many Planck units. And that a lot of people find distasteful. But that's okay. That's not the important message here. The important message is that the only explanation of slow roll inflation is in the same category of explanations as the explanation of a cosmological constant. It is part of the story of structure formation, or perhaps the wrong story of structure formation. But now I want to come to another question. Given this curve, what's the probability that the number of e-foldings is between 60 and 63? Now, 63 is a number that I sort of arbitrarily picked, but being between 60 and 63, about 3 e-foldings is the range of number of e-foldings where you have a chance of looking back and not having all of the signals of a pre-inflationary era. By pre-inflationary, I mean pre-slow roll inflation. Slow roll inflation tends to stretch everything out, it tends to dilute everything, and it tends to make it impossible to look back to what came before. The only hope of seeing what came before is that the amount of slow roll inflation is relatively close to the empirical bound, within a few e-foldings. Is that likely? Well, with the same silly model, you find out that the probability is about 0.1. Not very likely. I'm afraid that most likely the answer is going to be that there was too much slow roll inflation to see what happened earlier. Nevertheless, the stakes for me are high enough that I decided to explore the phenomenology of what would happen if the number of e-foldings was within this magic range here, where it would be possible to see things not diluted from before inflation started. Now, the logic is not so different, although particle physics won't necessarily agree, with supersymmetry. Why do we assume supersymmetry is at a TeV? Because that's where we can see it. It's a little better than that, but and I think this particle physics argument is a little better than the cosmology argument. But this is a prayer that we live in here, because if we don't, it's going to be incredibly hard to find direct evidence for any of this picture. Okay, what are the possible direct signals that could be visible? And of course, where I really wanted to start was starting about here and telling you how to organize data using conformal field theory techniques and so forth, but I think I won't do that today. The first thing is that if we are in that magic range, then the number of e-foldings is not so large that it would have completely wiped out any evidence of negative curvature. In other words, we should be able to see that the universe, the spatial universe, is negatively curved. This, incidentally, is a picture of a negatively curved space, a uniform negatively curved space. It's the Poincaré disk. It's also Escher's drawing called limit circle number 4. If you want to really entertain yourself, you want to hypnotize yourself, go to the internet, look up limit circle number 4, and stare at it for an hour, and you will find yourself completely insane. Try to figure out how Escher could have done that. I mean, when you recover, you want to do it. It's addictive. It's very addictive. You know, if you're trying to recover from drug addiction, do this, but it's probably no better. All right, so the detection of curvature. The curvature of space has been measured to reasonably good precision. It's less than 1% in some units, but I'll tell you precisely what that means. Incidentally, curvature is the square of the inverse radius of curvature. That means when you say that the curvature is very small, maybe you ought to take the square root of the curvature to find out how big. Wait, let me go back a step. Supposing we wanted to detect the curvature of the Earth. If we want to detect the curvature of the Earth, then we don't want to go out on a field 100 meters by 100 meters. It's just too small to see the curvature. We want to get out on a field 100,000 meters by 100,000 meters and try to detect very carefully any curvature. And the same is true in the universe. If you want to detect the curvature of space, you've got to be sampling a big enough portion of the universe in relationship to the radius of curvature. All right, so what we know from observation is that the universe, that the horizon of the universe, or that the radius of curvature of the universe is at least 10 times bigger than the horizon size in the region that we can see. That's all, 10 times bigger. It's not 100 times bigger. It could be 100 times bigger. So we know that the amount of inflation that took place was enough to make the radius of curvature of the universe at least 10 times bigger than the horizon size, or better yet, just the size that we can see and that we'll ever be able to see. So we need to be able to detect curvature better. I am told by people who are in the business that the curvature can definitely be measured to another factor of 10. Now, how hard that is, I don't know. But the claim is in the next decade or so that the curvature will be measured to another factor of 10. And I don't know if they're going to see anything. Probably not. They'll probably just see flat. What I do know is that if you see positive curvature at the level of 10 to the minus 3, there's something wrong with these ideas. So that means that positive curvature would falsify these ideas. Being a experimental, I don't say it would falsify everything here, but it would falsify this particular package, or the package as a sum total. So curvature is the first thing to try to detect. If the curvature is detected, that means that the number of e-foldings was not so big that it obliterated everything else from very early on, and we have a chance of seeing some other things. Another possible thing that can be seen, and it's the data, and in fact, the whole subject that I really wanted to talk about in the first place, originated by trying to figure out how to correctly organize the data from bubble collisions. What is a bubble collision? A bubble collision just means another bubble nucleated somewhere near our own. Well, I think I'll come to it. Bubble collisions in our past are another signal. Again, they would be obliterated and wiped out by too much slow roll inflation. There are signals involving axions that I probably won't get into, tensor modes that I won't get into today in any case, but there are possible signals that would, what do I mean by signals? I mean that they would have imprinted on them information about the ancestor vacuum. That's the goal. Trying to find out what we can about the ancestor vacuum observationally. And these are various signatures that would have information in them about the ancestor. Why did I put that on there? I don't remember. Oh, spatial curvature. Yeah, that of course is positive curvature. You've seen that thing before. That's positive curvature, the surface of the Earth. And of course, as you know, out near the boundaries, positive curvature makes small things look too big. Negative curvature, yeah, and of course tradition is positive curvature. As I said, eternal inflation suggests negative curvature, and negative curvature looks more or less like that. That is a picture of negative curvature, and what it does is make far away things look too small. So there's a very clear and distinct observational difference between positive and negative curvature, and we certainly prefer one, but not the other. Now, how does it happen that large amounts of, in this picture, how does it why does large numbers of e-foldings make it hard to see the curvature? And the answer is, you take this disk and you imagine it being inflated by slow roll inflation. Then you ask and you say, once it's been inflated, you look back from our vantage point today, and you look back at the surface of last scattering. Think of this as the surface of last scattering. In other words, the place where the microwave photons came to us from. All right? And you ask, how much of it can we see? How much of it can we see within our horizon or within our observational region? The answer is we don't know, because we don't know how much e-folding took place, how many e-foldings actually took place. But at best, with the best and most favorable circumstances, if the number of e-foldings was about 61, which is one more e-folding than required by experiment, we would see out to something comparable to the radius of curvature of the hyperbolic plane. That means we could see evidence of curvature. we could see evidence of all of the things that would have originated from pre-inflationary periods. If a couple of more e-foldings took place, it means what we're looking at is some very, very small region of this curved space, too small to see any leftover curvature. So that's the problem. 64 e-foldings, I think, would undo us. 61, 62, maybe even 63 e-foldings, and we would have a chance of seeing the remnants of the earlier universe. Let's see, I don't even remember what's here now. Let me just see what's here. I think, okay, I'm gonna quit now. I've gone just about an hour, is that right? Have I? Yeah. So I think that's a good place to stop. And when I continue, I want to talk about organizing data by a method that is another one of these dualities. It's not a string theory duality necessarily, but it is an apparently correct duality between cosmology in one of these bubbles and, again, conformal field theory. I'll come back to it. That's what this picture is about. I think I won't do it now. That's the setup, and that's the things that I wanted to start with, and that I would have started with if I was talking to a group of people who are by and large my students. Okay. All right. I'm going to stop now.
That was wonderful. Let's have a few questions now, and then at 4 o'clock, the discussion will proceed on that point in the bistro. But I'm sure and let's start with the students, the Sci students, if you have questions or questions from non-experts.
Actually,
Yeah. What I did not gather was when the bubble starts at that vertex point, information from before that point we cannot obtain by definition. But
why not? No, the things that we can't obtain, at least by usual logic, is the things, had I continued this line down here, we cannot obtain information from here.
But you can obtain information from
here. The obstruction that's getting information from here is the large amount of slow roll inflation that might have taken place. Slow roll inflation takes place, let's say, between here and here. And signals coming in here get redshifted by that slow roll inflation. They can get redshifted to where, to the point where the signal of something interesting out here gets stretched to bigger than anything we can see. Yeah.
The reason I asked is that you said that an observer inside this bubble would look back and see.
That's this person over here.
Would look back and see a hot place where you came from.
No, well, yeah. You look back. Each one of these surfaces has a different temperature. Now it's kind of interesting. In the bubble nucleation phenomena, the universe really doesn't begin at this point over here very hot. The bubble nucleation phenomena is a very smooth phenomena, and it doesn't begin with an enormous amount of radiation. It pretty much begins just plain empty. And the only thing that keeps it from being empty is the slow roll inflation that took place from a somewhat later time. In some period of time which is called curvature dominated, where the curvature term in the FRW equations is bigger than the vacuum energy. And then it doesn't even know that it has any vacuum energy. So in some period, slow roll inflation begins, let's say, over here, ends over here. In here, just emptiness, pretty much.
Back on your probability slide where you were showing 57.5 e-folding.
Which should, of course, not be taken seriously. I mean, well, the 57.5 can be taken seriously, but the probability distribution.
Well, yeah. But my question was with the 57.5. In order to get a prediction like that, what kind of a definition of structure are you using? Because you said like galaxy formations.
I think dwarf galaxies is what they're,
Okay, so you're basically saying that in order for anthropic principle to hold, there have to be galaxies and the rest follow from there. Okay.
And I think we were conservative and said at least dwarf galaxies.
Okay.
Question over here.
So actually, I had maybe a related question, which is for the numbers of e-foldings, do you expect to get any information from the power spectrum on any of this? I mean, is the difference between 61 and 64
I don't see how.
something that adds a feature changes?
Well, I don't know anyway.
And maybe another way of putting it is suppose you find, you know, from dark matter annihilation or something structure on solar mass scales. What is that? How does that change the
I don't know. I don't know. I don't know. I don't know. But I think you could be asking a general question. Do we already know that the number of e-foldings is larger than?
Yeah.
Yeah.
Is
I'm told not. I've asked that question myself, too, and I'm told no, that we don't really. But so.
Even if we can choose the magnitude of the
Say it again.
even though we can choose the magnitude of the cosmological constant, but how to explain today the magnitude of matter is closer to the magnitude of the cosmological constant.
How to explain the
magnitude of matter is closer to magnitude of
the accidental, almost approximate agreement between. I'll refer you to a paper, which I find a group of papers that rather than try to summarize them, I'll just refer you to the papers. There's a paper by Raphael Busso and his collaborators. What is it called? And I forget the name of it. It's fairly recent, and it's on the problem of measures. And do you know the Busso and Harnick and
Gilad Peretz. Gilad Peretz also one of them.
yeah.
I don't remember the name, but it was one of the recent papers.
Yeah.
But just look for
Right.
Peretz and Busso.
Right.
The papers wrote together.
Right, in which they make what I consider an interesting argument, and the other group which comes to exactly the same conclusion for very different reasons is Guth, Vilenkin, and Garriga, I think. Guth, Vilenkin, and Garriga, and there I think it's called scale factor measure, it's a paper called scale factor measure. And in those papers, there is the seeds of an argument. Of course, it's an attempt to find a measure for the landscape, and it's purely phenomenological. There is no real underlying theory to it. But in there is the only explanation that I know of why this conspiracy between orders of magnitude. I'm going to leave it to that because to start explaining it now would take me another hour. But read the papers by Busso and collaborators and Vilenkin, Guth, and Garriga, I think. Yeah.
Okay,
There's
question.
I have a question about the sort of predictability,
about what?
the predictions that sort of come out of the model, because you can accommodate anything. If you see something very weird tomorrow, you can cook up sort of a series of transitions that would say that, oh, okay, so now I can accommodate that as well.
Hopefully there are things you can't accommodate. What can I say?
But there are definitely things that cannot be accommodated.
What can I say? So what? First of all, is it really true that you can accommodate anything? I don't think you could accommodate a world without gravity. I think there are probably
Within the parameters that you have for life to exist, whatever.
Yeah.
The universe does something funky, something comes into your horizon which is sort of out of the ordinary, but you can still have something to explain it in your mind. I mean,
Look, there is a danger that these ideas will get wildly out of control because of what you say, that the number of possibilities is so overwhelmingly large that everything becomes totally unpredictable. Possibly. I don't know.
So for example, just to be more concrete, one test of the anthropic argument for lambda is to look at very small galaxies, which are formed at high redshift, say redshift 10 or more.
Right.
And if you can see within these galaxies stars like ours and heavy elements like we know are needed for life, then if you see them there, and if you find planets like ours, which seem to be enough for life, then the point is when those galaxies formed, the lambda was completely irrelevant. And so doesn't that undermine the case that lambda's important?
Okay, so I don't know.
That's a prediction. So it's claimed we should do the measurements.
Yeah.
If we find conditions suitable for life, that disproves.
You're right, but it's also interesting that the version of the arguments given by Garriga, Guth, and Vilenkin, and also Busso actually don't depend on structure formation. It's another generation of argument which actually don't depend on it. So I just gave the simple-minded.
Even for the lambda, they don't depend on it?
Pretty much, yeah. Yeah, it's pretty remarkable.
What do
It's whenever you make that
if I told you, you'd either hit me, regurgitate, what they depend on is the coincidence between the time scale for biological evolution to take place and the basic scale that sets all these things is the scale of biological evolution. Yeah. Yeah, I mean, these are serious people. These are not idiots. That's never a good argument.
Okay. Another question or two? No. Yeah, in the front here.
My question is, you said that there was no real way to tell whether that plateau in the landscape of slow roll inflation had bumps in it, effectively, if the rate of change of inflation was changing very, very gently.
Yeah, I think that's right. I think
Because I mean, my thought is, if there was a way, like your anthropic principle argument, if there was a way to tell if we had bumps in that landscape and we could still survive and be, then surely there would be. There's a good chance that there would be bumps in the landscape if there could be bumps in the landscape, and that should be something that we should be looking for. Does that make sense?
Definitely.
So evidence against bumps would be evidence against this picture. What would be evidence that there were no bumps?
Yeah.
Between 60 and 0 would be evidence against the picture. I don't know.
If you want it to be, okay.
And that's what it depends on sort of the rate of change of curvature of that landscape, but chances are.
I think the answer is there's no reason not to believe in bumps. Of course, you don't want a bump which is a bump which prevents you from going through it.
Yeah,
right.
I mean, small deviations.
Yeah. I think maybe perhaps even natural explanation, the natural expectation would be bumps.
Isn't it, I mean, there should be then, if there were bumps of inflation, I'm sure there should be some.
Well, I don't know. Then you'd have to really get serious talking about, you could talk to string theorists. What kind of models do they make for this evolution, this inflationary potential? Does it have bumps? Doesn't it have bumps? And again, my guess is with enough work you can find almost anything. So I don't know. I think that's well beyond what anybody knows of the texture of the potential beyond the first 10 e-foldings or so. Is that right about 10 e-fold? Yeah, 10 e-foldings is the
From 60 down to 50.
Yeah, and that's pretty flat.
Below there,
Yeah, it could be all kinds.
but it's measurable. It is measurable. High rate.
You have to measure the high
small scale.
What do you have to measure?
The structure, linear structure on very small scale.
Small angular scales. Yeah, lots of small angular scales. Now, right. And, I wouldn't try to make a prediction about it.
Okay. Let me ask a last question, maybe looking forward to the discussion. The measure problem, to what extent do you think this is a question of definition of the theory, that is, what is the inner product, and to what extent the question of what state?
I'll say what I said in the beginning. I think the biggest Achilles heel, potential Achilles heel of this whole subject would be if no underlying principles can be found which fix probability. The whole, I think we just don't know enough. I think I just prefer to be silent about it.
Okay, on that unusual moment.